specific problem. Now, it is good to, and today I want to start the class just by going over 4 different perspectives, which I see them as being equivalent when we deal with a problem, when we deal with a specific transformation. And these transformations, sometimes they might be transformation in space, okay? And sometimes they could be transformation in numbers, okay? Or in, which can have a geometric representation or space representation. Now, let's start with these examples and let's see what we're going to talk about. And always, all of these 4 examples that we're going to provide them on the board, they have a relationship with 2 major components that we're going to discuss in this class, because we said that this class has 3 major components. The first one, it was to deal with specific problems which are mostly related with computational complexity. The second part was to discuss about the Fourier transform and the wavelet transform. So we consider this one the second block of the class. And the third part of the class, it will deal with applications of advanced linear algebra in data analysis. And this data can be 1-dimensional data or 2-dimensional data. And now, what we're going to see now, we could view this one as equivalent problems that relate, let's say, linear algebra and let's call it transforms. Okay, when we say transform, let's see what types of transforms we're talking about. So, this is the board. So our examples, they will deal mostly with transformations. In general, I'll say what I mean with this one. The second topic that I want to go over is the unimodular matrices. The second transform is that I want to talk about one transformation which we can often see in the and the 4th type of transformation, this would be, maybe I could have switched the 3rd and the 4th. This would be the analytical mechanics. Now, so I promise you that we're going to provide a few insight of how linear algebra and how Fourier transforms or general transforms are related to these 4 topics. So regarding the first one, what we can say is that we have this type of transformation. We can consider this Galilean transformation. Now, how complex could this be? This is not complex at all. This is in fact, sorry, I believe you cannot see the top of the board. We can fix this. Now, the Galilean transformation is simply a change of reference frame. Okay, it's not that tough. So you can preserve an orthogonal coordinate system. So you can view this one as if you have this coordinate system, and then you want to project a specific data set in an updated coordinate system. And when I say updated, probably a better looking one. I have an example that we often provide is the following. If we have a data set which are distributed like this, we can choose a better coordinate system, which we can bring it like here. Okay. So this is one example of how we can have a certain transformation in space. Let's call it in space. Very soon, we're going to observe that a distribution of data we can automatically, without considering the geometric representation, we can do this one using the singular value decomposition, this SVD. We're going to discuss this one a little more in detail, but I just want to kind of remind all of us that this is the geometric representation, which can also be represented by a Galilean transformation. And the simplest transformation is this one. You are observing an object that is moving in front of you, and all you can do is that you can change the angle where you are looking at the problem. So you can move, let's say, 30° with respect to the object that is moving in their reference frame. That's one possibility how you can define this transformation. And here we also observe the same. We have some data set which probably this data set is changing from x 3.2 up to x 4.6. Okay, this is the distribution of the data. And here we have also, let's say, from 1 to 7.4. These are just some random numbers to show how the specific data set is changing in two orthogonal coordinate systems. For better representation, what we could do, we can take this data, we can calculate the singular value decomposition, and what we do is that we just shift the whole coordinate system and we send it where we see it over there. Now, so we are kind of changing the reference frames. Okay, we're changing reference frames. Okay. When you do that singular value decomposition, you are going to remember what we are discussing right now. Now, these changes in reference frames often will include rotations. Okay, and these rotations, we can represent rotations by matrices which can be they can look like this, and a simple one can be cosine theta minus sine, and cosine. Okay, so here we have one rotation, and these rotation matrices, for which over which we can adjust the reference frame, these have determinants. So determinant, we denote this one as an absolute value. We can say determinant of r. This would be plus or minus 1. Okay. In fact, plus 1 with regard to what we are discussing right now, the Galilean transformation, which is just we are just rotating the coordinate system. It is more correct, I can add this one, that considering the determinant equal only to plus 1, it is more correct, but from the broader perspective, we can consider this one to be plus minus 1. And in fact, any matrix which has a determinant plus minus 1, these are denoted as unimodular matrices. So let's have a term, which probably we have heard this one, but if the determinant is absolute value of 1, these are called the unimodular matrices. Let's call this one matrix. Okay, so this was the first type of transformation we wanted to discuss. Now, the second type, we immediately, so this was what rotation is, we immediately come to topic 2, which is we have the specific matrices which have a specific determinant or specific, or something that they generally do. Now, one thing that can become, so this was the first transformation, the second transformation, let's see what could this be useful for. So we have a matrix whose determinant is plus minus 1. Now, first of all, we look at this matrix. If the determinant is plus minus 1, that means that the inverse exists. Okay, that's the first thing. As long as the determinant is different from 0, we say that this is M is a matrix, so M inverse exists. This is good. But now, let me say right away, the use of unimodular matrices, it finds use in many different areas of science and engineering, including physics. But let's consider just one simple application of these matrices for number theory. Okay, in computational science, a lot of problems are based on the properties of integers. Even when in cryptography, often even being able to find out whether a number can be described as a product of two prime numbers. This is a huge, it's a very important problem, and but this is dealing with only integer numbers, so we're not discussing the value of pi or the value of e in this case. And then, since we're dealing with integer numbers, most probably we can find use also of this interesting property that this matrix can produce. So think about this one. I can put here number theory, which finds applications in cryptography, etc. So let me put it number theory application. Now, when we calculate the inverse, we have several techniques how to do it. One of them is the following. We have a matrix M, we write this one, this is matrix M, here it is, first one, this is the other matrix. How is this called? We call this one augmented matrices. And what we do some elementary row operations, trying to convert this M into an identity matrix, which is going to look identity. And this will be the M inverse, the inverse matrices. So if you look to basic linear algebra that you have taken since the first year, you know that we have done this before. This was one method using elementary row operations. Another method is the following. Given a matrix M, okay, what was the steps? The first step, we used to calculate the minors, okay? For anyone of us that does not remember correctly what is a minor is 1 minus 1, 2, 3, minus 4, 7, 11, 13, minus 9, okay? So the minor of this element is what? You remove this row and this column, and you find the determinant of what we have here, right? These are just things that maybe we don't always memorize. We open a book, we say, okay, oh, that was it, let's go ahead. So what is the minor of this element that we put here? So this is 3 minus 27, minus 27, minus 77. We get something like minus 114, I believe. Wait a second, so this is minus 27, minus 77, no, this is 104, minus, and so on. So we find the minors. After we find the minors, we multiply by minus 1 to the power I plus j, okay? I think we call this one cofactor. So this is the cofactor, minus, this is cofactor. And I think we find let this cofactor be capital matrix C. After this cofactor, we take the transpose and we find the adjoint. Okay, this is again something that you say, okay, there was such a thing. And this adjoint is equal to the cofactor matrix transpose. So we calculate the transpose and we get to this step. Then the final step to find the inverse of the matrix M, this is equal to 1 over the determinant of M, okay, times the adjoint, okay? So this is it. Now, imagine for a moment, we said that in number theory, for several applications that we are interested into, we want to deal only with integer numbers. So imagine for a moment that matrix M, that we start initially, it doesn't have a determinant 1, but we're just talking about in general. Let's say that the determinant of this matrix is 7. If the determinant of this matrix is 7, what is the probability of having a matrix M inverse which has only integers? For this one to be possible, imagine for a moment we have a matrix 3 by 3 or 2 by 2, and the initial determinant is 7. So let's make out a matrix M which has determinant 7. This is 3, 1, minus 1, 4. I believe this is true. So this is 3 plus 4, 7. So here we have determinant 7. The inverse of this one is going to be 1 over 7 times some numbers, right? Actually, probably some of you might even remember this. I think we switched 3 and 1, whatever. But it is a very small probability that these numbers here, they will be multiples of 7, so that when you divide with this one, you still get integers, right? So, so it's almost a small possibility, so we could have integers, only this was like 77, okay, 14, 28, minus 7. I mean, we don't always have, we're not this much lucky to get this, but things could get much better if we are dealing with unimodular matrices, which are things that looks like this. And I try to put an argument why this unimodular matrices can be useful in number theory or in areas of computer science. Now, here, I can write down a matrix which is a unimodular matrix, and this one it looks something like this: minus 1, minus 2, minus 2, 2, 1, 2, 2, 2, 3. Okay, 2, 2, 3. Here we have a matrix. This one determinant is equal to, let me see, what is the determinant of this one is 1. So it's different from 0. It is 1. It is unimodular. Things look good. And what we can use this to do is the following. we can apply this matrix A, which is a 3 by 3 matrix, which we can see it here. We can multiply this with a vector which looks like 3, 4, and 5. Okay, that's just an example. And what we get is the following. We get 15, 8, and 17. Now, I'm just going to jump back. What did we discuss here? We discussed a transformation which was preserving some situation, okay, which was preserving some equations of motion, which was preserving, we can put a lot of terminology here. Now here, the term is 1 minus 1. Here we have a matrix which is 1 by 1, and we are preserving something. I mean, probably there is some property of this triplet of numbers here, which are 3 numbers, and here we get another number. Now, in fact, if we have a close look to these numbers, what these numbers are, they preserve this property. 3 squared plus 4 squared, this is equal to 5 squared, okay? So we have a square, which is 3 by 3. We get the surface area here, plus 4 squared. This is equal to 5 squared. So this 3, 4, 5, this is 3, 4, 5, good enough. But if we check this also, we observe that 5 squared plus 7 squared, this is equal to 17, sorry, this is 8 squared. This is equal to 17 squared. Okay, that's good. So it looks like we have a unimodular matrix, which we apply onto an initial vector, and we get another triplet of numbers, and we preserve this beautiful property, which is, we can call this the Pythagorean triplets. So I can write this over here. So these are the Pythagorean triplet. That's good. Here we preserve some properties of maybe of motion, of space. Here we are preserving some properties in the number theory. And what we can do is that if we apply the A inverse to this vector 15, 8, 17, we get 3, 4, 5, which we get still numbers. But we can also apply A inverse to 3, 4, 5, and we should still get, let's say, the same. So the same property should be preserved, and I checked this before, it does preserve. Let's check this. Actually, we don't have the A inverse. I'm not sure if I have it. No, I don't. But if we apply this matrix A, again, on this other vector 15, 8, 17, what we get another triplet, which looks like this, which is 35, 12, and 37. And if we check this again, we obtain 35 squared plus 12 squared is equal to 37 squared, property preserved. And this was just another preservation of a specific property in number theory. Now, last time, when we were discussing about the computational complexity, we discussed I tried to discuss this one last week in detail. We said that if we have some property in the numbers, it might be good, it might be probably the best thing to do to obtain relationships for series that diverge to infinity in terms of the numbers. So in fact, this number, if we keep applying matrix A to the power 99 times the vector 3, 4, and 5, we know that what we're going to get is going to be another triplet. Of course, the numbers will be very high, but this property of A squared plus B squared is equal to C squared will be preserved. Now, the beauty of using the matrices, as we tried to argue the last week, is that this might have a very high computational complexity. It's a 3 by 3 matrix. It is to some degree, but we could even have a 5 by 5 matrix, and we might be preserving some property in the pentatlets of numbers. We can have 5 numbers. We want to preserve a property. No, we want to check how this property progresses when the numbers are too large, and then we can do this. Why is this useful? Because we can write a matrix A as a matrix S times diagonal times S inverse times 3, 4, 5, right? And now this we put here diagonal matrix to the power 99. If we have three numbers to the power 99, it's much easier to find. So, and then you just take 3 numbers to the power 99, multiply by 2 matrices which are 3 by 3, computation complexity is much less than this. And also, we can diagonalize this matrix, we know this for sure, because not all the matrices are diagonalizable. And if they are not diagonalizable, we can even use another trick, which is a singular value decomposition, which I briefly mentioned here, and about which we're going to spend a few sessions or a few weeks discussing for applications of SVDs. Good. So we just try to argue here that it is useful to use these types of properties or this type of approach of implementing the properties of matrix propagation through matrix multiplication or matrix to the power n, etc., to check what is going to go for large numbers. Okay, so even there are a lot of properties for prime numbers. We don't know whether these properties of prime numbers are preserved up to infinity. So far what we do is that we do brute force calculation. We put them in the computer, they're up for a long time, and you have some publications in Journal of Mathematical Computation, which are very good journals. The paper is 3 lines. They say that we tested this prime number is a Mersenne prime number, preserve this property. Done. That's it. Okay, they have 3 lines of paper, and they are super short papers, but they're in very good journals because they use supercomputers to check properties up to some specific numbers, and they try to beat the regions or the limits that they are analyzing. So here, this was the second example of how still we're dealing with these beautiful looking matrices or rotation properties or changing of the reference frames. This was the second example. Okay. Now we want to go to the electromagnetic field theory for a moment, and these calculations, I can take this away. This was on the board long enough, but so I think we remember this issue of the inverse matrices, how we find those. So we find that I join the setup. This was the example. And now, these types of transformation in space, often we may call these, so this one and this one, the first topic and the second topic, we call this, we can consider these are similar to this type of transformation, the gauge transformation. So, gauge transformation, the students of electronics engineering that have taken electromagnetic field theory might remember that the gauge transformation is a possibility to change the, for example, the equations. So all physics, it's about writing down this equation. F is equal to ma. Okay. Now in electromagnetism, we have electric field and magnetic field, where so this is for classical mechanics. Then, if we're talking about charges, we get something like this: QE plus Q times velocity cross B. Okay, and what we know is that the electric field is equal to the minus the gradient of a potential, and the magnetic field is written as the curl of another magnetic field potential, but this is a vector. This is a vector, this is a vector, this is a vector operating, sorry, no. This is just, sorry, this is something like this is a vector, 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 this is a vector. So this is electric field potential, it's scalar, with a gradient operator, we make this a vector, and this is the magnetic field, fine. Now what we can do is that we can change this potential V into a new potential V prime, and this magnetic field vector potential into some A prime, and these are done by this type of gauge transformation, and the physics or the equations of motions, they will be the same. Okay, so this is one let's say tricky, important, essential type of transformation that I mentioned this one when we covered the electromagnetic field theory course. Some of you might remember this, if we have taken this together. And now this gauge transformation, in Albanian we can call this like calibruese. We recalibrate the problem to make it better good looking, and maybe it's easier for us to solve it. I can assure you that in the future weeks we're going to solve several examples by just recalibrating the data or making it look a little better. And for this, we have some very good examples. Now, let's come back to this. This discussion right here, this was just to argue that the properties of what we learned in part 1, part 2, we can apply it now to part 3. So part 3, we come here, so we're talking about electromagnetic field theory, EFTH. Now, we're not going to derive everything, but it's well established. Probably we are seeing these 4 different aspects in a single hour. You don't often see this one. I mean, you see all of these 4 important and probably slightly different from each other. You don't see them in 1 hour, or at least in 1 course, but we see it here. And what I can add here, but this is a formalism which is called the Lagrangian. Lagrangian formalism, it's a term which is in principle equal to kinetic energy. Like this. This is kinetic energy minus the potential energy. Okay, this is Lagrangian. This is what we call the Lagrangian formalism. And if it is written like that, I think we can do some justice to the electronic students. So this Lagrangian, it will have, it's an expression which depends on x, velocity, and time, and we represent this one as 1/2 m x squared. So this is the first derivative of x, which is the velocity, minus electric the charge. This is the potential, which is a function of x and t, plus e divided by the speed of light. But now I need some space. Maybe I can erase this part here. So here we have E times C times the velocity times the magnetic field potential. How can I call this one? This is the magnetic vector potential. So it's magnetic because from here we can derive from A we can get the B. I think this is all. I can write also on what A depends, but this is the Lagrangian of a particle, which is in an electric field, which we can see from here, and in a magnetic field, which is described here. And this x, sorry, I made this, no, this is a vector, this is another vector. Now, here we have one Lagrangian. Now, what do we use this for? We use this for to derive the equations of motion. So what is the equation of motion? I think we try to show it here. And the equations of motion, this is something like this. This is equal to ma. At the same time, this is m, second derivative of x. This is the acceleration. Now, equations of motion is going to look like this. Force is equal to mass times acceleration. This is equal to the charge times the electric field plus charge over the speed of light times the velocity of the particle. Cross product with, so this is the cross product with B vector. Okay, so I believe these are all like this. When electric field is pointing in a specific direction, the acceleration, it is in the same direction because that's the direction of the force. But when it comes to the magnetic field, the direction of the acceleration is not in the same direction with the velocity or with the magnetic field. This is something which is also obvious in this part, because the acceleration, it always has the direction of the force. Now, what we could do here with this gauge transformation is that we can recalibrate. We can, by changing, doing a proper change between the potential, we completely change the numerical values of this potential to make it d prime and this magnetic vector. So the vector magnetic field potential, we get this a prime, and then from this L, we can get another Lagrangian, which is L prime But still, even when we go to another representation, the equation of motion, it will be exactly the same, okay? And with the equation of motion, what do? We try to determine the path of a certain particle in a region which has both electric field and magnetic fields. As a reminder to all of us that took numerical methods, this is equivalent to solving a differential equation in a boundary condition problem. So, in numerical analysis or numerical methods in second year, you have taken courses where this is some x0, this is some x1, and you are trying to solve a differential equation with boundary condition, which might end up into drawing a curve like this. This is the same problem in when we want to analyze how an object moves under the effect of some external forces. So the solution of this is going to be something like this. Okay, it's a solution of a differential equation. And the beauty here, as if the equations of motions are the same, here the physics is also preserved. Okay? So here in number theory, we preserve the property of how numbers were related, right? Now here we are preserving the physics, here we are preserving the numbers, here we are again preserving the physics. Again, I can write down how these are going to change, but I might skip this one for now. I can give you my handouts. I can put them on Google Classroom, and we can have a look later again. Now, this was let's say, the third part, but as I said, I promised that I have to give to you the handouts. Now, we go to the fourth part. So this was the third one, arithmetic theory. Now we go to the fourth one, which is the analytical mechanics. Now, analytical mechanics, it's a very beautiful part. It's a very beautiful way to represent or to analyze motion, because all it does, it uses the symmetry of space. Okay, it's a very elegant way of deriving the equations of motion. When we can give so complex, for example, let's say if you have a couple of pendulums, you know what how the pendulums look like? They just oscillate back and forth. Here we have length M1, this is mass M1. Here we have another object. This is length L2, this is mass L2. Normally, writing down the equations of motion or finding the acceleration of this object, it is very difficult because we have to write the position x and y of this object as if this is oscillating. Okay, this is difficult because this is connected to a point which is not how do we call this one? Which is accelerating. So it's not an inertial frame. It's not an inertial frame. It is a non-inertial because this is under acceleration. So it's tough. But if we use the properties of the symmetry of space, this is a piece of cake. It is very simple, and we can give a couple of examples. But essentially, what we can say here is that when we do the analytical mechanics, we have two approaches. So we are discussing here part 4. This was the Lagrangian that we discussed in the electromagnetic field theory, which is this part here. This material was just for description. You can take this away. And now let's see what is this analytical mechanics related to. So we have a term which we call this the Lagrangian, and this is described as a function of x and velocity. So this is Lagrangian, and we have another formalism which is also very useful, which is here h is a function of x and k, and we call this one the Hamiltonian. So Hamiltonian, you might have heard this Hamiltonian in graph theory, I believe. So it is. I think it is inspired by the same group of people, a group of researchers that like these approaches of symmetry of space. I believe it's like Hamiltonian graphs or something, but I don't remember right now exactly. So we can derive the equations of motion. So actually this k, we can write this one as p. Okay, so actually this is the derivative of space, but this is velocity. So this is the Lagrangian, and this one is equal to the kinetic energy minus the potential. This is equal to kinetic energy plus the potential. But here, kinetic energy, we write this one as 1 over 2 mv squared minus the potential. This one, we write this one in terms of the linear momentum, which is p squared over 2m plus q. Okay? So, and we can derive the equations of motion from here, and we get very elegant solutions. Now, what is, let me think for a moment. Okay. Now, this transformation, we can always, it is easy for us to transform this representation to this one. And this is done using a transformation which is called Legendre transformation. Legendre transformation, what it does in principle, it is just try to represent the behavior of a system from the representation of x to the representation of a new variable, which is p. Have we ever seen this before in our class? Can somebody answer this? So we are trying. So we have a representation of a system in x domain, and we want to represent it in terms of p. Does anyone remember?
So yes,
Say it again, Gendy. I believe Gendy remember such a relationship, right? You presented something a couple of sessions ago. So what this is, the Legendre transformation, what it is doing so we know that when we take the Fourier transform, if we apply here a Fourier transform, we observe we have a representation of the data from x to frequency. So this would be, the Fourier transform, it can be, if it is time, we take the Fourier transform, we find hertz, we find the frequencies, right, which are inverse seconds. If we have a representation in meters, we take the Fourier transform, we find inverse meters, okay, which is something which finds applications directly in optics. It's not very obvious right away, but if we think and look at the equations a little bit, this is what we do. So here, we are kind of observing an equivalence between the representation from x space to p space. So we are completely changing the space to a conjugate space. We call this conjugate or reciprocal because it is the same way as representing a signal as a function of time, and you'll see how it is changing after each second. And similarly, you can take the Fourier transform, and you are observing now the frequency components, right? So it's something, so we can observe an equivalence between these. Now, the derivation, now I'm wondering whether we should cover first how the transformation is done. So the Legendre transformation, I think this might become a little tricky, but what could be helpful just for the moment, it could be an example to see how these two formalism, the Lagrangian formalism and the Hamiltonian formalism could be, let me see for a moment. Okay. So I have to erase some part of the material here on the board, but and what I will try to show next is just to see that what happens if we multiply some essential parameters here and here in these two representations, and let's see what we're going to find. Now, let's start with taking out this part. So let's do an example, and we know that the velocity square, it can be represented like this. So this is the velocity square. If we multiply by 1 over 2, m over 2, this becomes the kinetic energy. Now, let's consider this problem not in Cartesian coordinate system or not in x, y, z, but let's consider this one in polar coordinates. So if we write this one as x, sorry, if x, let's denote this one, yeah, x is equal to r cosine phi, okay, and y is equal to r sine phi. So then from here we can obtain that the velocity square is equal to the v square this is what we obtain if we are using in polar coordinate system, and the Lagrangian here, the Lagrangian formula is going to be equal to kinetic energy minus the potential, and this is equal to 1 over 2 times 1 over 2 m times r dot square, which is actually just the velocity in the direction of r. And in order to represent this one, let's assume that here we have a point, let's say that we have a particle that is rotating. So you get a string and you rotate an object. And what the object does is that this angle phi is going to change. Okay? And this one has a velocity in this direction. What is the velocity? How do we describe this velocity here? In this direction, this is r times phi dot. Okay? Because we know that the velocity here is, or we often see this one r times omega. And I'm pretty sure that in physics 101, you have seen this one. But now imagine also the possibility of this rope to be stretchable. So this rope is like a something that stretches. I cannot find the exact word, it's elastic. So then this means that we can have a velocity which is described as r dot. Okay? Which is the velocity in the direction, in this direction. Then we take the square, we find the hypotenuse. This is why this can be represented like this. Now, this was for demonstration purposes. Let's take this away. And we write down that the Lagrangian is this term plus r squared minus the potential energy of the system. Okay, you can still see that. Now, so this is this term, and from here we can derive the linear momentum. So now this is a property which maybe I'm just going to pass this fast because we may not have all the experience with Lagrangian formalism, but in principle, we can derive, we can say that the linear momentum of these two coordinates that are provided here, this is equal to delta L over delta R. Okay. So as an equivalent, this is something like this. We have L, it has the units of kinetic energy. So kinetic energy, it has units of 1 over 2 mv squared. This is a derivative with respect to the velocity, okay? with respect to the velocity. And what we get here, we get MV, right? We get a linear momentum. So this is just to kind of remind each other that this is really the momentum. And we have discussed this problem before, especially when we were talking about the Heisenberg uncertainty principle. But I believe we are comfortable when we see such an expression. And numerically, this is going to be the linear momentum, which is along the direction of r, along one coordinate. This is mr prime. Or this is the derivative with respect to time. This was one of the linear momenta. Now I can do this one a little more. And here we have the other linear momenta, which is along another axis, p2. This is the derivative of Lagrangian with respect to phi prime. Okay, so here we do the derivative with respect to the velocity or the rate of change of r. Here we take the derivative with respect to the other coordinate, because we should not forget that from x, y, now we are in r phi. Okay, that's why we do this. And the answer here is going to be m r squared times the first time derivative. So we have these two linear momenta, and then now I can erase this one because now we are convinced about what we have on the board. Now this was the Lagrangian. Then we said that we have the representation in the new domain, which it has an equivalent Legendre transformation, which we can see an equivalence with the Fourier transform. This is why we are coming from L to H in the domain of, which can be the conjugate properties can be observed in the uncertainty principle. This one is written as the linear momentum along the one generalized coordinate. This is plus E phi, the linear momentum along the angle, over 2m r squared plus u. Now, this is the Hamiltonian, and let me see for a second. And in this formalism, so we start with this formalism here and this one here, and in all of these results, we have a couple of important parameters, which I'm just going to write right away. So we have the determinant of this okay, so if we see this from this determinant, this is in fact a matrix. Okay, this is a matrix because we are taking the derivative of this expression here with respect to two different. I'm writing here the derivative with respect to xi and derivative with respect to xj, and we know that when I is equal, and since we have two coordinates, we have what? We have r and phi. So if you observe here, we have r and phi, and we know that when I is 1 and j is 1, we get one component of the matrix, right? When I is 1 and j is equal to 2, that means that, so here we are taking the derivative twice with respect to r, okay? Here we are taking the derivative with respect to r and then with respect to the, so this would be something like this. The second derivative of the Lagrangian with respect to r and with respect to phi. This is this representation, okay? Then if we interchange those, we know that the derivative is a linear transformation. Linear transformations, that means that if we have a matrix A, which is applied on a vector x, and then here we have a matrix B, we can interchange this by applying first the B on x and the A on, or at least the derivative has this property, okay? It's not always for every function, but derivative has this one. which means that this would be equivalent to the second derivative of L with respect to phi and with respect to r. So it's like in programming. So you are shifting all the possible different possibilities. So we have this. So this is 1, 1 in terms of this is 1, 2, this is 2, 1, and this is 2, 2. So this 2, 2, what this is the second derivative of the Lagrangian of L with respect to phi twice. Okay. Here we have the second derivative of the Lagrangian with respect to r, delta r, actually. I think this is also true. Yes, the formalism allows this. The formalism of the derivative. We all know this one. So here we take the derivative with respect to r, and here we have the derivative with respect to phi. This is also the same. So this determinant, which is apparently it's a matrix, this is going to be equal to here. So let's see here. What is the derivative of this term with respect to r twice? Wait a second, this is, no, okay, sorry, this is, again, sorry, I made a mistake here. These are derivatives with respect to the velocities, okay? I forgot this, but, so let me repeat this again. What would be the derivative of the Lagrangian with respect to the velocity along the r? Yes, r dot, actually, r dot. You get this one, right? Then, if we take the derivative once again, what is the derivative of this term? Would you agree that we get such an answer?
Oh.
Okay, so similarly, if we take the derivative with respect to the other velocity along the phi angle, we're going to get, and by the way, what is the derivative, the second derivative with respect to phi, and this is with respect to r. This is equal to the derivative dr over d phi of mr dot. What is the derivative here? This is 0 because we don't have here explicitly the first derivative of the angle phi. Okay. So we get a 0 here, and you can go over these calculations in detail. But what I want to show to all of us is the following. So the second derivative here is m. This is 0, 0, and this is the what do you say again?
MC squared.
Mr squared. Okay. This is mr squared, and then so this was. Let me erase this one. So this was a matrix which represents the second order derivative of the Lagrangian with respect to the generalized coordinates. Now we can also try to draw a similar notation, which is going to be, we want to see what is the determinant of the second derivative of the Hamiltonian. Now, this will be with respect to the delta PR, delta P phi, okay? So we want to take the derivative here with respect to these terms, okay? And if we do that, we're going to see. So if we do this one, we get the following matrix. This is 1 over n. This is 0, 0, 1 over mr squared, I believe, yes. Now, why do we get this one? So you can have a look at this expression. If we take the derivative twice with respect to p phi, initially we get 2 p phi over 2 mr squared, right? This cancels out. Then we take another derivative with respect to this one, we get only 1 over mr squared. We get this, right? Now, again, we multiply this with this m0, 0, mr squared. Wait a second. So what is the determinant of this matrix?
Yes. Identity matrix.
Yes, we get one actually. Okay. So we get one, which means that we have, in principle, by doing this Legendre transformation, what we are obtaining, we're getting a representation, which is kind of the inverse initial representation. A couple of sessions ago, when we had a presentation from the students on Fourier, on the uncertainty principles, we mentioned something like if you have MC term, we can also take 1 over MC inverse term, and we get some interesting properties, which would be equivalent to taking the Fourier transform to get a representation of different ranges of masses, okay, objective and mass of Kushner. This is what we can do. Now here I can leave this one this much. Of course, there are much more details which we can go in detail, but my main objective was the following: was try to understand how when we do transformations in space or to represent the equations of motion of a specific system, if we follow one type of transformation, we always observe relationships which are similar to this, like delta x times delta p. Now this is larger or equal than some constant, okay, that's fine. But we at least learn that these are inverses of each other. And this is true, because if we increase delta x, this one will be decreased, because this side is a constant. Now, an equivalent principle is also observed here, and yeah. So here, we have the transformation, which preserved everything. It was purely rotation. Here, we observed that we had unimodular matrices to preserve some properties in number theory. We preserved the determinant, it was equal to 1 or minus 1. Here, we checked that it was possible. Actually, we didn't cover this one in detail. We just said that we had some gauge transformation. So in fact, maybe I can add here what type of transformation we do here. So this can be simply a rotation. Okay. This one, this is rotation. So this does not only rotate actually. This rotate and changes the magnitude. So I can see here magnitude changes. Why we say that magnitude is changing? Because if we have 3, 4, 5, the 5 is a small number. But if you do the next number, it was like 15, 8, and 17. So we observe a vector in 3-dimensional space, which is increasing. Okay, so this is because we know that in 3-dimensional space, if you have 3, 4, 5, you know that it's 3 units along the x, 3 along the y, and 3 along the x, 4 along the y, 5 along the z. So we can define a point in space. If you apply this matrix A again, you get 15, 8, 17, which is again a vector which is a little further in 3-dimensional space, but we preserve the specific property. So we say here, we rotate and we change the magnitude, and we saw how this was possible. In electromagnetic field theory, we do what do we call this? A gauge transformation. I'm just going to write a gauge. Here we have the Legendre. Now this Legendre, it's to some degree, it carries an equivalence with the Fourier transform that we have seen before, and the equivalence, actually, the equivalence was seen probably, it represents itself in here. Sorry, this one, I was looking for this one. So this kind of representation here and this one, they carry some similarities in a few different domains. Okay, so this was just some, how can I say, this was just some interesting approach that I just wanted to share with you in order to, let's say, to awaken the intuition about different aspects of what we are doing. Some more details, especially for the second part, we're going to see in the third part of the course when we do in detail the singular value decomposition, or when we analyze the the eigenvalue decompositions or the singular value decomposition, the SVD and the eigenvalue decomposition. Do you have any question for what we did so far? I just want to check the settings. Video. Okay. Okay. Any question?
Adesso cambio di scatetta e cioti, che dia mi gioco mio io.
Io non credo un po', Andrea. Okay, that's good. Okay. I have a question. Does V make you simple? So this V, you mean the scalar potential, right?
Io dite Lagrangian. Scalar potential. Se vedete, ma coordinate volte Lagrangian prime.
Yes.
Oh, le prime. Puoi calibrare, ma calibrare nel bidimensione, e ne ho una potenzialità due parametri that fallen
Genti, this is a good question. So the way that the potential and the A change, I can write it here, but you know, I saved some extra details. So the Lagrangian, let's see how it changes. So the way that let's say the V is a function of x and time, and this x, it's a it can be 3 dimensions, x, y, z, right? This is a vector. And this one, we can update this one into Vx, which depends also on time, minus 1 over c, the time derivative of the scalar value, which depends as a function of x and t. Okay. Now, the vector A, which is the magnetic field vector potential, this is a function of x and t. This the transformation that is done is from A, we get A, which depends on x and t, plus the gradient of some scalar potential, a function of f as t. So now this is how these are modified. So here we have a gradient, which is going to look like this. This is a vector, scalar, 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 okay, vector, scalar vector, because the gradient, it turns out. So this is how these are changed. Now, the thing is that you are saying, reading the comment, so does L prime gets calibrated in 2 different dimensions from A? Actually, when you say dimension, it can be 3D, 3 dimensions, okay? Because even this gradient, I can say the following. So this gradient in Cartesian coordinate system, I think you know pretty well. This is something like ax d over dx plus ay. It's something like this. Ay d over dy plus az d over dz. Or for general, at least for simplified, if you consider just the Cartesian coordinate system, this is the I, J, and K. Now, similarly, this gradient can also be the cylindrical or spherical coordinate systems. So for spherical coordinate system, this is going to be something like A capital R d over dr plus A theta 1 over R sine theta. But this is the part when we need the formula sheet or the cheat sheet. And here we take derivative of d over d theta of r times the vector that we are going to include here. Okay, this is just the operator. Plus, you know, we have also the a phi and so on. So I can write the whole thing, but okay, can I leave like this, Genti?
Och sen har så mycket så här dimensioner kopining. Jag har 3 dimensioner fysik för dimensioner kopining kategorin broschyrer.
No, that's okay. This is a good question. So I think we remain in the X space. We don't go to the conjugate space. So we can use this couple of terms. So when I do the Fourier transform, we can consider the following. So this X or time, we can apply either one, okay, X or time. We apply Fourier transform to go to the conjugate. We can call this conjugate space, or we can call this one reciprocal space. Reciprocal called space, and here we get, so let me write this one, we get a quantity which is meter inverse or hertz, so this can be frequency. The frequency, we can write this F, and this
is a wave number.
K. That's K. This K is equal to 2 pi over lambda or 2 pi over x, and this is how, yeah. So your question then, I understand, when we do this type of Legendre gauge transformation, we don't do a transformation that is like this, okay? We just change the coordinate system, which would be equivalent to a rotation, because we are still in space, okay? We're still in x, in the x command, and everything depends on the value of x. Was I, okay, I hope I answered this. But what is really amazing, actually, the most beautiful part of the formalism of Lagrangian, which uses the symmetry of space to derive the equations of motion, this is a really very elegant one. It is much simpler than anything that you have seen in Physics 101. It is much simpler and much beautiful. Okay, any other question? If we have no more questions, we can stop this recording.